Welcome back. In this part, we're going to discuss how to create your own classes in Java. So again, Java is an object-oriented programming language. Java supports object-oriented programming by allowing you to create classes. So it's a class-based object-oriented programming language. And classes basically just allow you to define your own user-defined types. The reason that you want to do this is because not everything is a number, an integer, or a double. Not everything is a character or a collection of characters, a string. Instead, real-world objects, like say a student, they're composed of multiple pieces of data. They've got a name, they've got a birth date, they've got an address, etc. And so we want to be able to model that. We want to be able to model real-world entities. So to show you how to iteratively build your own class, I'm just going to go ahead and start with a demonstration here, and we'll start with a student class. So I'll go ahead and create a new class called student. And in Java, a class name, again, is upper camel cased. We avoid pluralization because it's one instance. We might have a collection of students, but just one instance of a student, one student, or one object that represents one student in the real world, that's just a singular object. So we try to avoid pluralizations. We try to label them as accurately as possible, just like we do with variables. So what is a student? Well, a student, like I said before, has a name, right? A first name, and a last name, say. And you can get into, suffixes, you can get into middle names. I'm going to keep it simple for now and define my student to have a first name and a last name. Well, what else defines a student? Well, they could have a GPA, which is going to be a double. And they could have a lot of other things. For example, let's say a date of birth or an address. Let's go ahead and go with a date of birth first. So what is a date of birth? How do we model a date of birth? Well, it's a date, right? So it has a year, a day, and a month. So we could do something like this. We could represent all those things with integers. Month, day, and year. Or we could represent the entire thing like a string. Say, for example, some formatted string like that. There are lots of ways that we can do this. Let me go ahead and keep it simple, and let's consider this design where I've got a month, a day, and a year. Now, each one of those things is a separate piece of data, but it represents a single entity, a single date. And if you've got a situation where you've got a collection of data that is associated with one general object, then that should send off a red flag in your mind with your design that maybe I should be defining an object for this. So what I'm going to do is I'm going to take these three things and move them over into another class. And now over in the student, instead of having those three separate pieces of data, I'll have one piece of data that represents a date of birth. Now, another aspect of design is that when you take a real-world object, you decompose it into its constituent pieces of data, like we're doing right now with a student: first name, last name, date of birth, GPA, etc. But there has to be a stopping point. At some point, you get down to where it's so simple that you have to represent it by a single number or by a string, like we did with first name, last name, and GPA. Or it's screaming out to you to design another object, like, in this case, date. But another aspect of design is that you don't reinvent the wheel. If you've already got an object that represents what you're trying to model, then use it. And in Java, we've got a local date. It's in the java.time library. So I'm not going to go ahead and reinvent the wheel. I'm going to go ahead and get rid of this class now that I'm not using it. Right? And I'll show you how to use the local date later on when we're actually building an object. But one thing that we do want to represent that is not built into Java is maybe an address. An address is a street, city, state, and zip, right? And again, these four things represent one object. They're just components of another object. So I'm going to take them and move them to their own class. This is not only good design, but it is also good in practice because it allows you to reuse this class. Maybe we want to create a bank account class, in which case we would reuse this class because the owner has a bank account, the owner is a person. Maybe the bank itself has an address. And so if you find yourself using a particular set of data more than once in more than one place in your program, that probably means that you need to design an object to do so. All right, that's pretty good for now. We could design some other things to go along with our student, but I want to keep it simple for demonstration purposes. Let me go ahead and go back over to the demo, get rid of the code from before, and let's go ahead and I'm going to go ahead and show you how you can now use this object. Once you've got a user-defined type, just like an integer, double, string, whatever, then you can go ahead and create your own instances of it. Now, this is not an instance yet. This would be like creating int x. What value does x have right now? Well, it's indeterminate. It may have a default value if you, depending on how you declare it, but it has not been. The variable itself has been created, but that's because it's a built-in primitive type. How do we create a student here? Well, the way that you create user-defined types is through a constructor. You need to, similar to what we did with arrays, you need to use the new keyword. And this right here is an actual method, even though over here we didn't write any methods yet. That's because in Java, by default, if you don't define any constructors, a default no argument constructor will be provided for you so that every object can at least be created. We'll talk about constructors in more detail here in a moment, but at least now I've got my student object. If I print it out to the standard output, I just get this meaningless string here that has nothing to do with the actual object. It's a fully qualified package name, and then this is actually a hex code indicating the Java virtual machine memory address at which it's stored. We haven't set any of its values yet. For example, what's the student's first name? What's the student's last name? So let me go ahead and set some of those things. Now we can use the same dot operator to access individual member variables. These things over here, these are variables that were not declared inside of a function or inside of a method. That means they were declared inside of a class. That makes them members of that class. And this class, each instance of this class owns its own copy of those variables. So if I create two students, they'll have their own first name variables. And they're different. We can have a student named Chris and a student named Jane. So let me go back over here and use the dot operator to access those. I'll go ahead and set it to my own information here and give myself a perfect 4.0. But I'm not. I won't worry about the address here. But what is my date of birth? Well, if I just go s.date of birth, right, I'm accessing another object. And it turns out that I've got a bunch of methods that I can call on that object, but I don't have like a date that I can set, or a year that I can set this to 1990, whatever my birthday happens to be. Instead, I need to create this object just like I created the student up here on line 21. The way to do that in Java is to call this function of, and I'll go ahead and put in a year. That's July 9th. And now I've got my date of birth. Right? And again, I won't worry about the address just now. So let me go ahead and run this again. And again, we get the same meaningless memory address. And that's because that we haven't specified that, if I were to print out a number or if I were to print out a string, Java already defines how those things get printed. So over here in the student, one thing that we can do is we can create this special method called toString. It returns a string. It's called toString. And when we do that, whatever string we return, whenever we print something to the standard output or convert our object, our student object here, to a string, this method is responsible for doing it. So whatever we define in this method, if I say just foo and come over here and run it again, of course it'll print foo. That's not what we want. What we want it to do is to print out this object's state. In other words, this object's first name, last name, maybe their GPA, maybe their date of birth. So what I'll do is I'll go ahead and format this as a last name concatenated with a comma, concatenated with first name, and I'll go ahead and just use date of birth here with a space in between. And when I do that, now I get my last name, my first name, and I never specified how to format this date here, year, month, day. That was done by the toString method in this object, in this local date object. So this local date object also has a toString method that we call it overriding this method because it exists in every object. Its default behavior is what we saw before to produce that Java virtual machine memory address. We're overriding that functionality to provide our own custom functionality here of don't print out that Java virtual machine memory address. Instead, print out the first name, the last name, or last name, first name in this ordering. Okay. So now there is a problem here. One of the problems is that there's nothing to stop me from resetting these values. If I printed this out again, then it'll be Joe Burke instead of Chris Burke, right? So it's not apparent that that's immediately a problem. But what happens when I do something like this? I set it to an invalid value, null. But that's not a valid value, right? So if I want to control the values that you set, and I want to reject null, there's no way that I can do this because I've made all of my variables essentially public, right? There is actually no visibility keyword here which makes them package protected. We'll talk about that later. But all of my variables are open to the world. I can set them up here. I can reset them down here. I can access them. If I just wanted to print out my last name, right? I can access them. I can set them. I can do whatever I want with them. This is because the visibility is open up to the outside world. You don't want to do this. If you allow your objects to have public state, like I've done here, essentially, then any piece of code can change your state. If any piece of code can change your object, then you have to test for the eventuality that every piece of code will eventually change your state. It's kind of chaos. It opens it up. We want to make sure that we can restrict access as much as possible. So what I'm going to do is I'm going to come back over here and change the visibility. I'm going to make all of these things private. And I could cut and paste, cut and paste, cut and paste. Or I could learn how to use my IDE a little bit better. And I will go ahead and put this into what's called block selection mode. You can then, in block selection mode, you can, instead of selecting line after line after line, you can actually select blocks. And what I did is I selected a block that was, I selected a column, and then I started typing, and it types the same thing in every column. That's block selection mode. For the quick keys, look those up on whether or not you're using a Windows or a Mac or something like that. I've made them all private. Now, that didn't change much of anything over here in the student class, but over here, it did. Now accessing these from the outside world, we're in a different class now. I can no longer do this. It says that the field is not visible because I made it private. By making it private, only the class itself can see it. Only the student class can see it. So I can no longer do it like this. So I'll go ahead and get rid of these things. And now it's fine. I can't access the first name. But let's see what happens when I actually print it out. Well, I get a bunch of nulls because I never set those things. So now this comes back to a constructor. By default here, we're just creating this object. In other words, we're just allocating memory for it. We're not actually setting the first name, the last name, etc., etc., etc. So how do we go about solving this problem? First of all, I really want to print my last name. So if I try to do that, again, it's going to be invisible to it. So it's not going to be visible to us because it's private. So what I'm going to do is I'm going to come over here to student, and I'm going to enable the outside world to access the first name, the last name, etc. But I'm going to restrict access in that the outside world can't reset those things. Right? So let me go ahead and show you what I mean by creating what's called a getter. Now I've introduced some new syntax here. This dot. This is a key word that allows an object to always refer to itself. This object. And you need that because if I've created a student representing myself, Chris, I'm inside the student class here. How do I represent that? I can't. Over here in the demo, I'm referring to this is supposed to model me, I'm referring to it as S. But over here in the student class, there is no S. Right? There's no way for it to refer to itself. So the way that we enable that is by creating this keyword, right? And then I can say this object's last name. Go ahead and return that. And over here in the demo, what I can do instead of just getting the last name, which would enable me to change it, make it mutable, then I'll go ahead and use that getter instead so that I can print my last name. Of course, I haven't set it yet. It's still null. I'll show you how to solve that problem here in a second. But before I do that, maybe I want to enable somebody to get the first name, the GPA, the date of birth, the address, etc. So maybe I want to type a bunch of code for all those getters. People call that boilerplate, and they hate it because it requires a lot of typing. Oh no. Well, they never learned to use their IDE properly, because if you go up to source, you can generate all your getters and setters with a click of a button. So I'll go ahead and expand all these. You can have a get and a set. In other words, if I want to enable the outside world to change the last name, it's not showing get last name here because I already did it. I could do them all, I could do none of them, or I could just do the getters, which I'm going to do, and I'll generate the code automatically. Right? So all that boilerplate is taken care of for you if you know how to use your IDE properly. So get last name, get first name. Now over here in the demonstration, I can do this. Why didn't I do the setters? Because again, I wanted to restrict access to the outside world. One good design principle is to make all of your objects, whenever possible, make all of your objects immutable. Remember, the strings are immutable; they cannot be changed once created. Well, once this student is created after this constructor here, then nobody can change their last name. Nobody can change their first name. And that might seem limiting at first. I'll show you how. Again, we'll define our own constructor here in a moment. But immutability is a very, very good thing because if you're programming in a multi-threaded environment, and everything is a multi-threaded environment nowadays, you've got multiple threads accessing the same pieces of data, the same object. If both of these threads can read and write the same object, then you have to synchronize them. In other words, you've defeated the purpose of having multi-threaded programming, or you've made it more difficult. But by making it immutable, then that means that these threads can only read the data. In other words, they can't step on each other's toes. So you get thread safety for free by making everything immutable. Okay, so those are all the getters. Now, again, if I printed this out, then it's all null. Right? That's because I didn't give myself a way to actually set these things. Setters are a way of doing that, but a much better way of doing that is to create your own constructor. I'm going to create a constructor that allows you to set the first name and the last name. All right, so first name is equal to first name. Last name is equal to last name. So a couple of things to note here. First of all, a constructor is different from other methods in that it doesn't have a return value, and it has to have the same name as the object itself. That's because you don't need a return value. When you create something, if you're creating a student, it knows what it's returning. It's returning a student. If you are creating a bank account, it knows that it's a bank account. If you're creating a string, it knows it's a string. So there's no return type necessary here. Constructors always are always named after the object, and they can take as many parameters as you want. We'll create another constructor here, a different constructor in a second, but for now I'm only going to do first name and last name. And it's highlighting this as a warning here. If I highlight this, it says the assignment to a variable first name has no effect. That's because there are actually two variables in scope in this method that have the name first name, right? The instance variable itself, the member variable, and the parameter variable down here. Right? It would be like creating int x, setting it equal to 10, and then x is equal to x. This line has no effect. It's basically taking the value that's already in the variable and then putting it back into the variable. And that's what the warning is telling us here. It's because this first name and this first name, they're both referring to the parameter variable right here. What I need to do is I need to disambiguate this. In other words, I need to say, I want this first name to be set to the value in this first name. To do that, I need to use the this keyword, this dot, this dot. Now they're different variables. This first one refers to the instance variable, the member variable up here, and this one refers to the parameter variable. Now I've got a compilation error because in Java, if you don't define a constructor, a default no argument constructor will be provided for you. But once you define a constructor, that default one goes away. And so now now there is no such default constructor anymore. I need to pass in my first name and my last name. And when I do this, that gives me a way of setting these things, right? So that I can set them when they're created. Immutability ensures that I can never change them again. If I try to do that, it'll be a compilation error. Right? But that I can still access them either through the toString method, or if I want to explicitly get the last name, then I can do that as well. Now, in this demonstration, I only did the first name and the last name. Probably you'd want to do everything. You'd want to do GPAs, date of birth, address, etc., right? I'm going to have to type. I can have more than one constructor if I want. I'm going to have to type this all out. Again, more boilerplate, or I can trust my IDE and have it do my work for me. Generate constructor using fields, all of them. Go ahead and generate that for me, and great. And over here in the demo, I can actually use that. My GPA is 4.0. Right? My date of birth was, I'll need to use local date. And I will need a new address. Because I haven't really developed that class yet, I'll go ahead and create a new default address that doesn't have any values, since we're not printing it out anyway. But as a matter of fact, let's go over here and let's follow the same design principles. I will make everything private. And with a few quick mouse clicks, I can go ahead and generate everything I need. Generate a constructor to allow you to create something with all four of those pieces of data. Generate a bunch of getters if you want, so that you can get each individual piece of data. Right? And you can also generate your own toString method using the entire state. And it'll do it for you. Now, the default is not going to look very nice. It's just going to label every single piece of data and then print that value out. So what I'm going to do is I'm going to now change it. At least it gives me a starting point, though. There. Now over in my student, I'll go ahead and now print the address as well. Remember, it went away. And these things can get kind of long. There are ways to solve that problem. But when I do this, now I get all the state. With only a few keystrokes, I was able to design my object, stub out all the boilerplate without having to type too much code. The only things that I needed to type are where I wanted it to be customized for, say, printing out the street address here. Right? Again, it's getting quite long. You can always break onto the next line if you really want to. There are other patterns that you can follow. They're called creational patterns. For example, you can create a factory pattern that allows you to use a static method. For example, this is a factory pattern, right? Kind of a factory pattern right here, where you don't actually create local dates using a constructor. Instead, you use this static method of. There are other ways of creating objects. For example, you can follow a builder pattern. If you've got a lot of state to your object, and it can get kind of daunting to remember, well, was it first name first or was it last name first? You can follow those patterns to make your life easier. Let me go ahead and create another student here. Just to show you that S and T are indeed distinct instances. We call these instances of the class student. Student is kind of like a blueprint for how to create these objects that represent real world things. S and T are references to individual instances. Those individual instances have their own variables. The last name on S is different from the last name on T because they have their own memory addresses. They live in different locations in memory. They're their own objects. Creating them through the constructor, we call that instantiation. We're instantiating it. We're creating new ones. For one moment, I would just want to go back here, and we will talk about the single responsibility principle later on. But remember when we created the date of birth and the address, we could have put each one of those individual things in here. Remember that we had, say, a private int date, private int year, or day, year, and month, right? The reason that we didn't do that was, well, it didn't make sense if we can go ahead and create another object. We put that into another object because this is a student. This student has nothing to do with a date. It has a date of birth, and a student is defined in part by their date of birth, but it itself is not a date, right? It is a student. It's not a student and a date, right? So, one principle when you're designing objects is the single responsibility principle. In other words, an object should only have one responsibility. It should do one thing or represent one thing, and it should do it well or represent it well. If we've got another object that represents a date or a local date in this case, then we should use it. We shouldn't just put everything into one object. Everything should have a single responsibility. Student should know about student things, and local date should know about local date things, and we shouldn't mix those around. Let me go ahead and create one more student. So now I've got 3 students. I can go ahead and add these to, say, a collection, like an array list. Remember the parameterization? This is a list that holds students. I'll call it roster. And I'll add all the students to it. And I'll print them all out. The order that I put them in is the order that they get printed in. What if I wanted to sort them? And does that make sense? But what if I wanted a different ordering? What if I wanted to order them by, say, their GPA? I wanted Grace Hopper first because she has the highest GPA, then myself, and then Harry Potter here. Right? If I wanted to do that, I would have to sort them, right? But there's a problem here. It's complaining because roster is not naturally orderable. In other words, unlike unlike numbers where the natural ordering is in increasing order, right? 1, 2, 3, 4, 5. There is no natural ordering on student because it's a user-defined type. If you want to impose a natural ordering on it, you can do that, or you can make your own comparator. Let me go ahead and create another comparator like we did in our previous demonstration, but this comparator will be for students. It's parameterized for students. And the compare method here will compare the first student to the second student. But to do so, it needs to compare their GPAs, say. Remember, I'm using the getter here. If A's GPA is greater than B's GPA, then they should come first. And so they're in order, and I return something negative. And I'll omit the third condition here because it's either greater than, less than, or they're equal. And now if I pass this comparator into the sort method, it'll work. And now Grace is first, I'm second, and Harry Potter is third here. To do this, I was creating an external comparator. That means that it's still not naturally orderable. If I didn't pass in that comparator, I would have the same problem as before. It doesn't know how to sort those things because it doesn't know how to order them. Given these two students, do they go like this, or are they equal? So to solve that problem, if you really want to, you can implement not the comparator, but a comparable. And when you do this, you've now got a new method that you need to implement. I'll just go ahead and take this logic over here and move it over here. Except that I no longer have A and B. Now think about what objects you've got in scope here. You are passed in this student object, which we call S. I'll rename it S here. But what's the other object that you're comparing it to? You're comparing it to this student. You're comparing this to, say, that. Right? So we're going to compare this object, which refers to these variables up here, to that object, which refers to this object that's being passed in by as a parameter here. I'll call them this and that initially, even though that's not great practice. I'm just doing this for demonstration purposes. Now when I do this over here, now when I go back over here, you can see that the compilation error has gone away and that I get the same ordering as before. But I do so because I get this without a comparator because I'm implementing the comparable interface here. So again, it's not best practice to call an object that. S is not that much better, but I want to use this as a trick to show you that you can rename another IDE trick here. If I want to rename this, I can go down to refactor, rename, and it changes every variable within the scope automatically so that I didn't have to go and cut and paste, cut and paste, cut and paste. And same ordering as before. I want to show you one last aspect of creating your own objects. We kind of hinted on it just now with that functionality, but it's called encapsulation. So we've already got encapsulation here with respect to a student. In some aspects, encapsulation means that you're taking things and you're encapsulating them into an object or some sort of a unit so that you're protecting it from the outside world. Encapsulation involves three things: the grouping of data, which I've got right here. I've grouped this data here, which defines a student. The protection of data, and I'm doing that by making everything private, controlling access to it through these constructors and the getters. But third is the grouping of functionality on that data. Right? So what do I mean by that? Well, I've got another object here that I've already created, an airport object that represents an airport. Every airport has a name, code, and a latitude and a longitude. In other words, a location. Right? So I've got one airport. What if what if I had two airports? I had Lincoln Airport and Omaha Airport, and I wanted to determine what is the air distance between them. In other words, how far am I going to have to travel from one airport to another airport by air in a straight line in a straight line path? Well, if I don't use object-oriented programming, I could do a solution somewhat like this. So not using any objects at all, if I want to determine the distance between two locations, I could give them a latitude and a longitude, much like we did up here with Euclidean distance, an x and a y coordinate. If I did that, it would look something like this. I've got a latitude from location A, a longitude of location A, and then a latitude and longitude for location B. Now, don't worry about how to actually implement this. We're going to use the spherical law of cosines here, I believe it is. And I do need degrees to radians here. I'll bring that over. Because all the math stuff requires everything to be in radians. So generally, when latitude and longitude are in degrees, 45 degrees north, negative 120 or negative 90 degrees gives you west, right? And negative latitude gives you the southern hemisphere, etc. So I need to convert all of those things to radians. And then I can use the spherical law of cosines down here to compute. There we go. To compute the air distance between them. Again, don't worry about the details here. It involves Earth's radius, and this will be in kilometers. Earth's radius is 6,371 kilometers. Right. So if I did this in a non-object-oriented programming kind of way, then it would look something like this. Let me go ahead and get rid of all the student stuff. Well, the latitude and longitude of the Lincoln Airport, say, and the Omaha Airport. So Lincoln Municipal Airport is located at 40 degrees north and negative 96 degrees, that is 96 degrees west. And Epley Airfield is located at 41 degrees north and negative 95 degrees or 95 degrees west, right? So the distance between those two is 88 kilometers, which is the actual distance here. But the thing is, this is old style imperative programming. There are really no objects here. These are just a collection of numbers. They have no semantic meaning to us as far as, well, what do these represent, right? So here's another way of doing it. Let me go back to the distance utils. And let me change this so that instead of just giving it raw numbers, what if I gave it two airports? Now, what would that implementation look like? Well, it'd be very, very similar. But instead of using those four raw numbers, it now uses the getters, right? A.get latitude, B.get latitude, and longitude, and etc. Otherwise, it's the exact same value. Over here, instead of just dealing with four raw numbers, I can now actually create objects and model the real-world objects that I'm talking about. I could model the Lincoln Airport, and I could model the Omaha Airport. To do that, I'll go ahead and cut and paste over here. Lincoln Municipal Airport has a code of LNK, Omaha is OMA, and here are the latitude and longitudes. Right? So now I've got Lincoln and Omaha. I could go ahead and call the distance, instead of using this above, I will go ahead and call the other one where I pass in, instead of all these numbers that I have to deal with that have no semantic meaning whatsoever, I could say, what's the distance between Lincoln and Omaha? Right? And it works exactly the same I'm not changing the functionality here at all, but it is much easier for a human to reason about this code. Before, I was asking the distance between these two locations represented by this collection of 4 numbers over here. But now I'm reasoning about it with respect to objects. Right? Now we can take this an even step further. This is still an imperative style of doing things, of having a function that I want to know the distance between these two objects. Here you go, I'll give the objects off to something else, and it'll compute the distance for me and give me my result back. Remember, the third aspect of encapsulation is that you group the functionality that operates on that data in the class itself, right? This is not located in the class. If I go to air distance over here, I have to basically open up the object to get its latitudes and longitudes, and then I do my computation outside of the class, and then I give my result back. That kind of breaks encapsulation in that I'm locating functionality that acts on that data, the latitude and the longitude, outside of the class. So as a third and final solution here, let me go back to my airport class. And let me show you what it looks like to compute an air distance inside the class using good encapsulation. Again, for now, I'll call it that airport. Remember, we've got actually 2 airports in scope here. This airport that has name, code, latitude, longitude, and that airport that has its own name, code, latitude, and longitude. And without having to retype everything again, let me go ahead and take that functionality that was separated outside of the class and move it over here. And now how would we use this over here? Well, I've got Lincoln and Omaha. I would ask Lincoln, what is your air distance to Omaha? And I would get, again, the same answer here. But it's a little bit different design. Instead of doing an imperative design or a structural design where I take raw pieces of data and hand it off to another function and it does a state change or whatever and returns that stuff, or instead of encapsulating them in an object and only going halfway and encapsulating data without encapsulating functionality, I've gone all the way and I've encapsulated data and functionality together so that everything related to airports, including computing the air distance between one airport and another airport, is located inside the class. This is good encapsulation. So we will get more practice in subsequent videos on creating objects, and of course we will cover object-oriented programming in depth. The big 4, abstraction, encapsulation, which we've just discussed, and also inheritance and polymorphism. Just as a review for this part, remember that class names in Java are always upper camel-cased. That's a convention, not a rule, but it would look very weird if you went against that convention. Encapsulation is the grouping of data, the protection of data, and the grouping of functionality that acts on that data. All 3 of those things should be there for strong encapsulation. Any method that operates on an object's data should be inside the class. There's no reason to locate that get distance stuff outside of the class when it operates on data inside the class. Again, it forces you to rip open the class, pull out the data, do your computation outside the class, and then maybe put it back into the class or return it or something like that, whereas that should all be located in the class. Right? You shouldn't have your objects scattered over multiple different pieces of code. Variables inside of a class name are member variables, and they're usually lower camel case by convention. Member variables should generally be made private to protect that data. Again, that's part of encapsulation. And you can control that. You can control access to that through getters, setters, and constructors. This keyword can be used inside of a class to refer to the instance of the class itself. Again, because if I'm inside the class, I have no way of referring to myself. So if this is the object and I'm inside the object, I need a way to refer back to myself. Well, outside the object, I can have a reference to this, so a student S or airport A or airport Lincoln, right? Well, Lincoln exists outside the class. It doesn't exist inside the class. The name, the variable name doesn't exist there. So we need a special variable name inside that class called this. Instances of the class are instantiated by calling a constructor using the new keyword. If no constructor is defined, then a no argument default constructor is provided for you, just like a lawyer. If you cannot afford one, one will be provided for you free of charge. But the second that you create a constructor, or the second that you provide your own lawyer, then that free lawyer goes away. The default no argument constructor goes away. You can always restore it by explicitly defining it if you really wanted to, but that's kind of unusual. Use your IDE to its fullest. You don't have to do all the grunt work, boilerplate stuff by yourself. Let it generate code for you and then modify that code.